2 thumbs up, that's awesome. Yes, awesome. Good. I hope everybody enjoyed it. Yep. So, those who are the more observant of you may have noticed that this week is a scheduled quiz week. If anybody is curious about the topics of coverage for that quiz, it will be however much of interrupts we covered before the break, I2C communication, and real-time clocks. Those are your topics for the quiz on Wednesday, so study up. With respect to the midterm, some of you may or may not have seen the announcement. Actually, who has not seen the announcement about the midterm? Okay, a couple of people. So we're going to be having the midterm in class on Wednesday next week. We're going to have it through Avenue, so bring your normal means of filling out online quizzes. Okay? It will be a super duper secret hush hush operation with all the bags at the front, like normal. Actually, how many of you, you guys have all written a in-person midterm at this point, right? So you're familiar with the procedure? Vaguely?
Not in like a lecture hall.
Not in a lecture hall? Okay.
It was like a big lecture hall that was like much more spaced out.
Oh, like with the desks in front? Yeah. Yeah, so the procedure, we're going to have invigilators posted at both entrances to the room who will be checking off your names to make sure that you're, actually here. You have to actually be here in the writing room, in this lecture hall, in order to write the test. Anybody who thinks, oh, it's just an Avenue test, so I'll write it from the comfort of my own couch in my living room. No, you have to be in this room to write the test, because we'll be taking your Mac IDs there. So you have to come here. Essentially, you are to leave all of your non-test writing equipment and paraphernalia at the front of the room in a great big pile of backpacks. Find your seat. Absolute silence is to be maintained for the duration of the test. And, I realize it's somewhat tricky in a room of this size, but seating every other chair is required. And the test is going to be randomized in the same way as the quiz, so that it shouldn't really matter how many, it shouldn't really matter even if you do a sneaky peek of someone else's test. It's unlikely that the question they're working on is going to be one that you're even going to get. So it's just not a good strategy. Yes.
What sort of questions can we expect? Like multiple choice, short answer?
I've kind of stepped away from the short answer ones for the most part, unless it's really, really basic enter a number type stuff. But yeah, it's going to be primarily true or false and multiple choice questions with some of the multi-select questions as well. Very, very, very similar to the quiz format.
Okay, so
Just-
you can't expect any long answer type questions.
No, there won't be anything like that. Basically, it's just going to be a long quiz, but with a bit more time per question. And some of the questions are slightly harder than the new average difficulty for the quiz questions, which has gone down a little bit since the last quiz, since nobody did very well on it. So I guess we'll just have to, I'll just throw you the test, we'll see how you do, and if I have to curve it, then so be it. I don't actually curve things, though. I tend to reduce the denominator. Yes?
Can we have the quiz questions?
Can you what?
The quiz questions, like the database or the quiz questions, can we have that?
Like for the past 2 quizzes.
Yeah.
I've released the database of the quiz questions.
Oh, well, I've actually enabled it so that you can retake the quiz.
Oh, okay.
So I won't release all of the questions into the wild, but you can retake the quiz and it'll recalculate, or you'll get a different RNG roll on what questions you get. So cool. Yeah.
Yep.
Any other questions? Yes, sir.
Was the midterm open book?
Yeah. Yeah. Like, realistically, I can't prevent you from, looking at the slides while you're writing, right? Because you're doing it on your computer. So, the exam is going to be a different story. That wasn't directed at you, but you know what I mean. Any other questions? Yes?
So if it's open book and our notes are on our iPad, does that mean we can have both our computer and iPad, or do you have to split everything?
Yeah, I guess the whole leave things at the front thing is kind of overkill in this instance, isn't it? Yeah, okay. You can have your iPad. Yes?
For students with like SAS accommodations, what should it look like? Like, are we going to have extra time in this room, or are we going to go to like the SAS center?
You'll have extra time in this room. There's nobody booked in this room for at least another half hour after Wednesday, so we'll, that's, I believe, the maximum we have to deal with is a 50% bonus writing time, so I think that'll work out perfectly. And yes?
What does the content go up to, like the end of this week?
Yeah, the end of this week. Yep,
On the midterm, can we go back and forth throughout the questions, or we're stuck?
you're stuck. Yeah, that's an anti-cheating mechanism.
Yeah,
Yes.
that one
Like I
hurts.
hold my notes in a binder, so can I have like my binder like with me during the midterm then?
Yes, okay. For the exam, you'll get a double-sided crib sheet, so that'll be the aid during the exam. Any other questions? Yeah.
Can I use like Desmos as my calculator, or do I have to use the university calculator?
What's Desmos?
Like the online like calculator.
What
It just like adds numbers and graphs things.
Oh,
It's like a graphing calculator, but online.
you won't need one.
Okay.
Yeah. You won't need a graphic calculator. Any other questions? Yes.
Sorry, so you said that we won't be able to go back, so will it be like one question at a time, and we have to like time ourselves, like, so that we get all the questions?
Yes. Yeah. Yeah. Any other questions? You'll have more time per though than with a quiz. Yeah. Yeah, I know the not being able to go back thing really stings, but it's necessary. It's a necessary anti-cheating mechanism. So, because basically the thing that ensures that you guys aren't sharing answers using the electronic devices that you're working on is number one, tight time constraints for the questions you're working on, and number two, the fact that no two of you should be on the same question at once. So there's no reasonable, it would take too much time to cheat that you wouldn't benefit from it, essentially. But none of you are planning on cheating, right?
No.
Oh, there we go. Perfect.
That's double negative though. None of you are planning to cheat, no. That is a yes.
Well, so be it. This is our little game. I move my chess pieces, you move your chess pieces, and we'll see who graduates. So anyway, so with respect to lecture content then, we got a couple of things to finish up. Number one, we need to finish the economics slide set. It's got a bit at the end that's not economics related, which is going to be of interest. The other thing is we need to go back to interrupt and clean up just a couple of concepts because we did leave it unfinished. So hopefully we'll be able to get through most of that today, and maybe just a little bit overhanging on Wednesday. And on Wednesday I have a special treat for you guys coming up. So besides the quiz, no, I decided to make a few of the slides. So yeah. So the topic will be digital and analog conversion. So there was nothing good, so I was forced to pull together some pieces. Anyway, so last time we were talking about the economics of product development. We had reviewed several key concepts with respect to the economic factors of product development. Things like, what's your non-recurring engineering cost? What's your unit cost? How does this affect the profitability of a product given how many units of it that you are to produce? One thing I mentioned, which wasn't in the slides, is the compounding factor, particularly in electronics. Generally speaking, the more of something you order, the cheaper they come. And sometimes this effect is like, you can sometimes get components for like 1/100th of the price they would be if you were only ordering like 10 of them versus ordering 10,000 of them. So these it really is true that with electronics in particular, you really want to go for huge product runs, but that being said, if you produce 10 million units, you better be able to sell 10 million units because you don't get any money at all for things you don't sell. But at any rate, one of the key trade-offs that we have been discussing throughout the term is how things affect development cost versus unit cost, right? For example, programming in assembly language will increase the non-recurring engineering cost because it's a longer process, it's more tedious, it takes more effort to program in assembly versus a higher level language, but you can derive optimizations in assembly that are impossible in higher level languages, which can drive down your unit cost. A typical example is you may not require as large a memory chip you might be able to swap in a smaller memory chip which will save you a certain amount per unit, that type of thing. You want to be careful because it is definitely possible to overdo your non-recurring engineering cost, right? Particularly for, smaller product runs. So generally speaking, smaller product runs will favor higher unit costs and smaller non-recurring engineering costs. And long product runs, you want to get the engineering way, way down, refined to an absolute mirror polish, and because you want to spend a lot of money on engineering, and that will reduce your unit cost over time. This can a sort of an extreme example of this actually is Intel, right? So it's difficult to imagine a larger product run than Intel processors, right? They put those things everywhere, and they sell very, very large quantities of them. ARM process, like the processor itself, like an ARM processor, you're kind of in a similar boat. Intel spends a lot of money on things that wouldn't be feasible on products with smaller product runs, right? Smaller number of units produced. Things like formal mathematical verification. This is a process. This is actually a process that's related to my my thesis research. Formal mathematical verification is where you pay mathematicians to create a mathematical model of the thing that you're working on. Take that and put it into a deductive system, such as predicate logic or higher order logic, and then use that deductive system to produce mathematical proofs of correctness. It's an extremely expensive thing to do, but it does occasionally find bugs that can't be found by any other process. Since Intel is making, chips which are dominant in laptops and other, AMD is there too, but, lots and lots and lots of things have Intel chips, and lots of things which have Intel chips have very sensitive data. And if there is a bug, you know that some hacker somewhere is going to figure out a way to exploit it to be able to get at data that they're not supposed to get at. So bugs in that sense are a security risk. So Intel is justified spending these outlaying this type of money on the non-recurring engineering cost in order to, decrease the probability of these types of game-breaking bugs. Because when you have a bug in a CPU, there's really only one place to go, and that's to the next one.
Out of memory.
You're out of memory?
Yep. 0 minutes left to record. Do you have another SD card by any chance?
Oh, here. We're good?
Yep.
Awesome. So, anyway, for the benefits of posterity and the video, we ran out of memory, but I didn't really say anything that important, so we're fine. So let's shift gears a little bit. Now let's talk about the types of metrics that are used to sell products rather than the metrics that will allow you to recoup the cost. So everybody sort of, like when you're shopping for a laptop, for instance, what are the sort of things that you look for? What are the specs you look for? Anybody? Yeah.
The thing that says up there, the clock frequency, the instructions, like not the instructions per second, but the clock frequency is usually very labeled there, the RAM amount.
Yep.
Whether it has graphics, dedicated graphics, or like processor graphics. Yep. Speed of the storage.
Yep. Whether it's got a SSD or a magnetic drive, all of these types of things, right? So the problem is that a lot of these types of metrics are actually, they can be somewhat deceptive, right? Now it depends on whether you want to be a deceptive salesperson. You can sometimes make more money being deceptive, but generally it's not as good a long-term strategy. Things like processor frequency. We should know by now that there's not necessarily a direct correlation between how fast the processor is and how fast the thing you want to happen happens, right? It has a lot of factors that go into it. What operating system are you using? Are you using a Windows operating system? Are you using specifically a Windows operating system on my wife's laptop that was upgraded from Windows 8 to Windows 10 and has all kinds of programs that don't do anything that you have to disable from the startup thing, and they keep reestablishing themselves somehow, and it just is a terrible, terrible laptop, and I am so sorry that I suggested that you get that one, and it's just, yeah, it's just a whole thing, And so the clock frequency really doesn't necessarily have anything to do with actual performance. Any computer that's running Linux will perform better than any computer running Windows, just because Linux is a much lighter operating system, right? It's faster, right? So really, when you're talking about, but you know, these types of metrics were very, very, you know, it was common to talk about these types of things, you know, back in the 90s, you'd talk about how many floating point operations per second your CPU was capable of performing. You would measure things in megaflops and gigaflops, and nobody really talks about flops anymore. So what's a much more important metric than raw clock speed is how fast you can do the thing that you're attempting to do. So for example, how many pictures can your camera take consecutively? If you're, you know, getting one of those fancy ones where, you know, you want to do like the several still photos together so you can pick the good one, those type of things. And these days, a lot of people are like a lot more interested in the features that the operating system has than they, you know, things have kind of stabilized in terms of hardware to a great extent. But yeah, so what you're interested in are things like latency and throughput, right? So latency is the time between you requesting a task and that task being complete. And throughput is the number of tasks you can perform per second or per minute in some sort of, you know, per unit time, right? So, for example, some camera might be able to process 4 images per second. Some other camera might be able to process 8 images per second. So the throughput speed up of one camera versus another in that case would be a factor of 2. And, you know, you also have to keep in mind who your audience is, right? It doesn't make any degree of sense to focus on this type of thing if what you're making is like a consumer model point and shoot camera intended for children, for example. But if you're making like Canon photograph machines, what do they call those?
DSLRs.
Cameras. Yeah, DSLRs. For like, you know, sportscasters who take pictures of hockey players and stuff like that, then you want really, really high performance equipment, you know? So it really depends on what kind of bracket you want to sell your product in. But yeah. So with embedded systems, the manner of accomplishing a task, especially using technical processes, methods, or knowledge, is the technology. We have 3 key aspects of technology which we use in embedded systems design. Number 1, our processor technology, and we include in that all of these nitty-gritty little architecture details that we've been trying to ignore in you know, the slides on interrupts, for example. We have IC technology, which is the technology of how these peripherals that we've been talking about are put together, like the real-time clocks. And then we have the design technology, which is the act and process, the engineering process of combining the previous 2. You know, it's not necessarily like the sum can be the whole can be greater than the sum of the parts, right? That's what a good designer does. But yeah, any questions so far? Okay, good. So let's talk about processor technology. So I shouldn't need to explain the importance of processors, but at the same time, a processor is not necessarily what you need for all applications, right? It turns out that for very simple design applications, you can get away with more specific hardware, right? We have a continuum between general purpose systems and single purpose systems. General purpose systems can perform many, many, many different functions. Your smartphone, for example, great example of a general purpose system. It's general purpose to the point where software which is written for a laptop can be ported to it, you know, depending, you know, on a bunch of factors, but in general, something that's written on a computer can be put there. Application-specific controllers, you take the controller, you get rid of a bunch of the functions that you don't need, and you keep getting rid of stuff that you don't need until you have a thing that is still reprogrammable and still has some flexibility, but it's much smaller, much cheaper, right? So application-specific would be, for example, something like your Fitbit or a smartwatch, right? Still programmable, still capable of communicating with its, you know, what do they call those? Like, I want to use the word tethering software, but you know, it's like you have an app on your phone that the thing communicates with, and it communicates over Bluetooth, something like that. So, so the smartwatch is capable of some degree of reprogrammability, but it's a much, much smaller controller that has like much fewer functions, and as a consequence of that, much cheaper. Pulling that to its extreme, you have the single-purpose processor. These are often in hardware alone. You don't everything is in binary. Everything is a sequence of ones and zeros. You don't necessarily need a software solution to a control problem, right? You can do it explicitly and completely in electronics. This is the cheapest option for very large product runs, right? You design a controller, it's designed in electronics, you don't need programming, you just have a bunch of transistors on a board, there you go, resistors, capacitors, whatever, all of it. That can be produced for the lowest cost and thrown into an application, and you know, the thing you lose is any degree of flexibility. Once you have snipped off every piece that's not specifically dedicated to the task at hand, it becomes incapable of doing anything else, right? So if flexibility is what you want, general purpose. If low cost is what you want, single purpose. And if you want a compromise between the two of these, you go for an application-specific controller. Any questions? Yeah?
Now, just to clarify, for the single purpose, that would mean it's not reprogrammable, right?
Yeah. So when you guys, Aaron, you're taking 3TB4 right now, right?
Yep.
So you're doing FPGA design?
Yep.
Yep. So the design process often for these things, the design process for these guys, right? Although they are hardware and do not run software, they are often designed in a system that looks like software. These are called hardware description languages, right? So you do out a design of hardware which is written, it looks like C code, but if you think that it's C code, you're in for a rough time, you know, basically. It uses C-like syntax. So you do out your hardware design, you then prototype that board on something like an FPGA. An FPGA is reprogrammable hardware. We're not going to get into it in this course, but when you guys take 3TB4, you'll get into it plenty, trust me. This is a preview of coming attractions, right? So you take the FPGA, right? You flash your design into the FPGA. The FPGA can then be tested, and it's a hardware emulator, right? So any bugs there are in your hardware design will show up on a device that you can actually just make a modification in your design, re-upload it, and then, you know, test it to see if your bug is fixed. Because hardware can have bugs just the same as software. After all of your testing and quality assurance has been performed on the hardware design, you can then take that hardware design, send it to a manufacturer to be manufactured into an actual chip rather than an FPGA, which is still reprogrammable. You can do that, like that combines the flexibility of development on a general purpose platform with the cost benefit of single purpose hardware in the final product. Make sense?
Yeah.
Any questions? Yeah.
Where do you draw the line between general purpose and application specific?
That's a good question. So the question is, where do you draw the line here between general purpose and application specific? Well, in this particular case, they are talking about taking sort of the full CPU's ALU and register files and like just trimming functions off of it. So the answer is there's no clear distinction, right? If you consider the instruction set of, for example, the M4, the Cortex M4, it has, you know, I think something like 200 separate instructions. If you consider the instruction set of the Cortex M0, which is like the lightweight option, I believe it has something like 50, right? And because the size, complexity, and cost of the controller is proportional to the number of instruction codes that it implements, right? The size of the ISA, that's where your cost saving comes, right? Make sense? Any other questions? Okay. Good. So, so processors vary in their customization for the problem at hand. You can kind of think this is kind of like a somewhat facile metaphor, but it's a bit like set theory, right? The general purpose processor will be able to fit many, many different programs into it, right? The application-specific processor, less so than this one, but it'll still fit what you want. And the single purpose fits exactly and only the functionality that you want. We have some slides coming up in this course on digital design and the conversion of programming code to function block, or what's it called? FSMDs, finite state machine diagrams. And then you can take those and convert them to hardware. So we're going to touch on that a bit in this course, but again, that's more 3TB4 territory. We're going to continue our talk about how to wire up peripherals mostly. But yeah, anyway. So I think I've kind of covered most of this at this point. We've talked about what general purpose does. Again, general purpose. The name is pretty explicit. And single purpose, it's for a single purpose, yes. So, in addition to being low cost, single purpose processors tend to be faster and require less power, right? Because, you know, think about it, right? You've got a whole CPU pulling power. You've got like, you know, 50 to 60 transistors pulling power. Which of the two of those is going to draw more power, right? But yeah, I think this is the end of this section almost. Okay, so, and then of course application-specific processors. A programmable processor is optimized for a particular class of applications having common characteristics. So, you know, yeah. Again, some flexibility, good performance, size, and power. Some might even consider like the ARM processors themselves to be application-specific processors if you compare them to Intel chips, right? Because they have been optimized for, the sort of low-power applications typical of, things which have to carry their own power source. But, yeah, good. There we go. Cool. Any questions about that before we bounce back into interrupts for a moment? Yeah.
What side of District 5?
Say again?
What side of District 5?
I'm sorry, I still didn't catch that.
What side of District 5?
What's a register 5?
5. If you go back these 3 or 4 times. To general purpose processors.
Oh, a registered file.
Register file. Oh, I'm sorry, yeah. I think they just mean registers, like the regular CPU registers. I guess that according to some people, that's a file. I wouldn't consider it a file, but then again, I'm more like I would consider a file to be a file in the like desktop computer sense, which is not even necessarily like I would consider files to exist inside of the data memory, but yeah.
It's like a group of registers.
A group of registers is precisely, I think, what they're going for there, yeah. Any other questions? Okay. Good. So, let's jump back now, shall we? Dun, 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 dun. Dun, 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 dun. So, so we were talking about interrupts. We interrupted interrupts, and now we're back in true interrupt fashion. We are resuming main execution after having performed 3 interrupt service routines. Incidentally, they were all the same priority because none of them interrupted each other in order to be executed. So, so let's review the process very briefly. We have a program which is going along, doodling along, doing its thing. An interrupt is received, right? The processor enters handler mode. At the point of the interrupt, the registers, certain registers that are sort of the CPU, regular CPU registers, they're put on the system stack for later retrieval because they hold the program's current state and may hold the values of intermediate, like the intermediate values of ongoing calculations. Like, when you're thinking about this, you do actually have to think in assembly, right? You have to think a single computation, as I would consider it as a C programmer, for example, may occupy 10, 15, 20 lines of assembly code. An interrupt can come in at any point in that calculation, stop it, and require service. So it's necessary to save the data that is stored in the first 4 registers, register 12, and then a couple of other ones, including the program counter and the return register, the linking register. The link register is how you find the point in the program where you call the function from, if you're currently in a function call. So these things are pushed onto the system stack, right? So in another way of saying that, they are saved to data memory. They are then afterwards, after the interrupt has done its thing, they are retrieved during the unstacking process, placed back into their registers, and everything is hunky-dory. So, How many registers do we have in the CPU of the typical Cortex-M series ARM microcontrollers?
15.
Hmm?
15.
16. How many are we saving here?
4.
8. 1, 2, 3, 4, 5, 6, 7, 8. So in fact, half of them aren't even being stored. It's actually possible to send data back to the main program in register memory by having the interrupt service routine write something to, for example, R6. But, normally, it's easier to just load, have the interrupt service routine send things into data memory. But of course, since this is an embedded systems application, we have to talk about doing everything with registers and assembly programming, because that's, requires less memory. Yes?
Sorry, what's XPSR and PC?
So, PC is the program counter. So that keeps track of which instruction you're on in instruction memory, right? That has to be preserved so that you know what point to jump back to in the program. I believe this one tells you which stack you were using of the two stacks. We talked about the two stacks, right? You guys remember that? Yeah, okay, good. Yeah, make sense? Yeah. R12 and the rest of them are just general purpose registers. Good. So this is what that process looks like. These X's here, that's like the current top of the stack, although it's actually the bottom, but we've been over this. It builds down rather than builds up, so everything's reversed. But anyway, so that's the existing stack. We pop all of these elements onto the stack, and then we have the new stack pointers. So one might say, how do we know where we are in the stack? Well, it turns out that there's a register for that called the stack pointer. The stack pointer points to the current end of the stack. You can access, basically, when a program is loading data from a stack frame, it's always it's looking for a particular position in the stack frame and then offsetting it by the current value of the stack pointer to get at that actual frame, right? So the stack pointer, of course, also has to be updated. Make sense? Good. So, yep. So I think this is just, yeah. I already talked about this, but we'll go over it very briefly. There are actually two stacks that you have to worry about. The main stack pointer is used primarily for kernel operations and is used to support operating system operations. The process stack pointer is used for user programs. This allows you to, it provides better support for operating systems, which is not necessarily a thing that you have to worry about with ARM processors, but for a smartphone you definitely do. Yes?
What's the difference between the thread versus handler, processor nodes?
A thread versus a handler. Oh. So a thread is, it kind of gets into operating system stuff, not discourse kind of stuff, but very, very roughly. How do CPUs handle multiple programs executing at once? That's sort of the general question, right? The answer, you have several execution threads which are going on at once, right? So let's say you're on my computer, I've got this, PDF viewer open. That's running its own. That has its own thread, right? My antivirus software, which I don't need because I have Linux, that's running its own thread, right? Processes, if they want, yeah.
They're handling multiple things at once, which is why it's called the thread.
Yeah, so like thread mode versus handler mode, thread is like the regular threads that would be generated through regular execution. Handler, I believe in this case means specifically like the interrupt handler. But yeah, so
We just need to know the difference, like, because on the previous two slides, it said like thread mode and then handler mode when it was like mode and interrupt.
yeah,
We just need to know that like it's in those two modes when it's dealing with it.
yeah, you don't need to know about threads and stuff. I'm sure you're gonna take an operating, you guys take an operating systems course, right? Yeah, you'll learn about it. So I won't belabor the point, but threads have become very important in recent years because now CPUs have multiple cores, so you actually have multiple CPUs that can each be operating on an individual thread. That's all I'm going to say about it. Processes can spawn multiple threads. That makes parallelism work. Okay, all right. We're going to skip this slide, skip that slide. Stacking and unstacking, already talked about it, but very briefly. You stack you put all these registers on the stack, then you pop them off when you're finished, put them back where they came from. Oh, there you go, handler mode and thread mode. There we go. So thread mode means working on main, working on anything that's called by main, working on any processes that may be spawned by main, all of that kind of stuff. Handler mode is just for interrupts, right? So,
And we use the LR to like indicate the difference between the two.
yeah, so there's a special assembly command called BL, branch link, which is what is actually used to jump to a function, like the start of a function, right? So when you perform a link branch, the LR register is set to the instruction after the branch, right? So let's say you have execution, you have a BL statement that jumps to, function 3, right? And then you have, add R0, whatever, and then continues on, right? When execution hits this statement, it then jumps to function 3, executes that, and then when it returns, like this is what a return statement actually is, right? When it returns to the statement the statement after the branch link, right? While maintaining all of the data that it needs to actually return the value. So so yeah, that's the link register. The link register LR at this point receives this address.
Receives the add R0 address.
Yeah. Yeah, like if this is address, 837, and this is, 836, Make sense? Cool. Yeah, okay. I think that's it for today. See you on Wednesday.